I want you to just picture a cruise ship for a second.
Mm-hmm.
I mean, we are talking about a 100,000-ton steel skyscraper, basically floating on water. It just feels like it shouldn't work.
It does create a bit of cognitive dissonance, doesn't it? It just feels like it should tip right over.
So how does it stay upright, especially when a massive storm is trying to knock it over?
Well, it's not magic, as we're going to see today. It's pure, unadulterated physics.
And to figure this out, we're doing a deep dive into a technical breakdown for marine engineering. It really deconstructs the science behind ship stability.
And our mission, really, is to decode that perfect balance.
Mm-hmm.
We're going to try and uncover the invisible forces that are constantly fighting to keep a ship from capsizing.
Okay, so let's start with the basics. Calm waters. The source describes this as a state of equilibrium. You've basically got a tug of war happening, right?
That's the perfect way to see it. You have two major forces. First, you've got gravity, or G.
Right, that's just the weight of the ship pulling straight down through its center.
Exactly. And then pushing back up from the water, you have buoyancy, which we call B.
So in a stable ship, those two are just a straight line. Gravity pulls down, buoyancy pushes up.
And they cancel each other out. The ship just sits there, perfectly steady.
But, the ocean is rarely flat, so this is where the physics gets a little messy. A gust of wind, a rogue wave hits, and the ship tilts.
And this is the critical moment. When that ship tilts, its weight doesn't actually change. The center of gravity, G, stays exactly where it is.
But the part of the ship that's underwater, that shape changes? If it tilts left, the left side digs deeper and the right side kind of lifts out.
Precisely. And because that underwater shape has shifted, the center of buoyancy, that point pushing up, it moves to the side.
So now they aren't lined up anymore. G is pulling down in the middle, but B is pushing up from the side.
And they've created a lever. The source calls this the righting lever, or GZ. This separation creates a rotational force.
A force that literally shoves the ship back upright.
That's it. It's an automatic correction.
The source used this great Tamil term for this, Faliati Bamai.
Which is that traditional roly-poly doll.
Yeah. It's such a fitting comparison. You push the doll's head down and its internal weight just forces it to pop right back to the center.
A ship is basically a massive steel roly-poly doll.
But engineers, they can't just hope it works like a doll. They need to measure it. And that brings us to the Metacenter, or M.
Yeah, and this can be a little hard to visualize.
It felt a bit abstract in the source, I have to say.
Think of it like the pivot point of a pendulum. If the pivot, M, is high above the weight, which is G, what happens when you push the weight?
It just swings back to the center.
Exactly. So that distance between the pivot and the weight, we call that GM. You want a positive GM, meaning the pivot is above the weight.
And if M falls below G, it's like a pendulum with the weight on top of the pivot.
It flips over.
Capsized.
Instantly.
Yep.
The higher the GM, the stronger that swing back effect is.
Yeah. Okay, this is where the source noted something that really surprised me. It said this number gives the ship a personality. You have stiff ships and tender ships.
And there's a huge trade-off here. A stiff ship has a high GM. It's very, very stable. It snaps back upright incredibly quickly. It's safe.
But if I'm a passenger on that ship, that snapback sounds absolutely miserable.
It is. It's a jerky, violent ride.
So wait, you're telling me if I'm on a cruise and I'm spilling my drink because the ship is jerking back and forth, that actually means I'm safer?
In terms of pure physics, yes. Contrast that with a tender ship, which has a low GM.
That sounds nicer.
It feels nicer. It rolls slowly, lazily. It's very smooth, very comfortable.
But that's a trap.
It's a dangerous trap.
Yeah.
In a bad storm, it lacks that strong muscle to snap itself back upright. Comfort does not equal safety out on the ocean.
Now, we can't talk about this without talking about what goes wrong. The source flagged the free surface effect, and this seems like it actively sabotages everything we just discussed.
It's a hidden killer. Imagine a fuel or water tank that's only half full when the ship starts to roll.
All that liquid sloshes to one side.
Right. It's like trying to carry a wide pan of water while you're running. That shifting weight artificially raises the ship's center of gravity.
And you want that weight G to be low, so this sloshing pushes G up.
It shortens that pendulum arm we talked about. It makes the ship much easier to flip over.
Drastically reducing your safety margin.
Which is why things like ice building up high on the deck or loading cargo improperly are so dangerous. Anything that shifts weight the wrong way is fighting against the ship's natural stability.
So that giant iron tower isn't just defying gravity by floating, it's actively fighting it, using its own geometry as a weapon.
It's a constant invisible dance between the weight of all that steel and the shifting force of the water pushing it back.
So next time you look at a massive ship, Don't just see it floating. Try to visualize those invisible levers.
Constantly at war, pushing it back upright against the chaos of the ocean.
An amazing thought. Thanks for listening to this deep dive.